All right, here we go. Let's see how this is going to work. So we've already talked about this problem. We're trying to find the shear force and bending moment at point C. So I'm going to start the problem by cutting the structure just to the left of C. Okay? And when I do that, I'm going to draw my free body diagram, and we're going to look at the right-hand side. As we talked about before, that should make our workload a little less. So let me draw a free body diagram for that. So I'll give my beam a little depth. And now on that side, I'm going to draw positive axial force, positive shear force. I'll even put a little plus there to remind you that these are positive. And then here's my positive bending moment. Everybody see that?
Yes, sir.
So then I'll have my three forces. Now since I'm cutting it just to the left of C, this 500-pound force at C is there. I didn't give myself enough room, so I'm going to write it in the bottom. It looks a little unconventional, but it will behave the same way. And then out here at point E, I have this applied moment. And just to make the units match up, remember that one's in kips and one's in pounds, so I'll make that adjustment in the diagram, and that's 10 feet.
Why did you flip your moment?
Oh, thank you. I didn't mean to do that. Thank you, Mr. Romero. All right, so what do we do now? Let's sum moments. So I'll use positive sign convention, right-hand rule. So I'm going to sum moments at the cut and equal to 0. So what kind of moment with my sign convention is this internal moment? Positive or negative? It's negative. So negative moment. What about this 500-pound force? Does it create any moment about the cut? Remember, we're so close to it that it's basically the moment arm is effectively 0. So there's no moment created by this force. Remember, we're summing moments about the cut, right? The cut plane. So then this one will create moment, and so will this one. And they both create what kind of moment? Positive or negative? Negative. So I'll have minus, I'm going to change that to kip. So I'll have half a kip force at 10 feet and another half a kip force at, what's the moment arm there? 20 feet. And then down here on the end I have the applied moment, which is also negative, and that's 2 kip feet. So I solve for the moment. It looks like it's going to be negative. I have half of 10 is 5, half of 20 is 10, that's 15, plus 20 is 17. So that's 17 kip feet. Everybody see that? Yeah. That's not so bad, is it? So now I'm going to zoom up for my sign convention, and we're going to try to get the shear force by summing forces in the y direction. Now, since I'm assuming my forces are up positive, this shear force is also up. Then I've got 1, 2, 3 500-pound forces acting down, right? So I'll say half a kip, half a kip, half a kip. So when I solve for the shear, what do I get? 1.5 kips, and looks like it's positive. See how easy this is? Nothing to it, right? I guess I'll finish it off. This is not necessary every time, but if I do sum forces in the x direction, assuming right is positive, I would get a negative a value, but I have nothing else. So it doesn't matter. Axial force is 0. So now what I want to do is I want to make a cut to the right of C. So I'll go back and label that. This was the left side. And now I'm going to do it again with the right side. So not only will we get some practice, but we'll kind of also investigate what it means to pass under an applied force. So now my free body diagram is going to look almost the same. So I'm still going to have my positive shear force, my positive axial force, and my positive bending moment. Now, this 500-pound force, since I cut it just to the left, see, it was there. But now I'm cutting it just to the right, it's not there anymore. But I still, 10 feet away, have my 500-pound force. Another 10 feet away, a second 500-pound force. And hopefully I'll draw it right this time. This moment of 2 kip feet applied at the end. And the length still 10, the length still 10. So let's see how this affects our results. So again, I'll come over here and I'll sum moments about my cut surface, which is now shifted to the right of C. Right hand rule in equilibrium. So I start with my moment. You can see it's a negative moment using right hand rule. Each of the 2 500-pound forces are also negative. So that's half a kip at 10 feet, minus another half a kip force at 20 feet. And I just ran out of space there. I'll try to tuck it in. Minus 2 kip feet. Sorry about that. That's the applied moment at the end. So if I sum moments, what do I get? It says the moment is minus 17 kip feet. So it doesn't look like my bending moment changed much. Right? Here it was to the left, and here it is to the right. So you don't get any kind of instantaneous change in your bending moment when you go underneath a force. So moment's going to be kind of smooth. It's going to be kind of continuous. But let's see what happens with the shear force. So I'll sum forces in the y direction, assuming up is positive. So what do I have? I got positive shear force up, minus half a kip down, minus half a kip down. So my shear force looks like 1 kip. Now what's changed? Well, it was 1 kip to the right, but it was 1.5 kips to the left. So what changed in the shear? Well, it was 1.5. It's to the left, it's 1.5, and then I pass under this 500-pound force, and it changes by that amount. See the difference in the two? So it looks like the change in shear is equal to that applied force. That's just an observation right now. I have no theoretical background to claim that. It's just, hey, look at that. That's kind of interesting. We'll prove later that it's true. That your shear force will change instantaneously by the amount of the force. So that means magically my shear on the left side is 1.5, and then I move this almost zero amount of space and it drops to 1.
But that's only true to a point, right?
At a point load. So I could actually kind of make some notions of this and kind of plot it. So if I did plot the variation of my moment with X, and let's assume I have some denotes where C is. So just to the left, I don't know what the moment diagram is going to look like or how it changes. Let's just say the moment is coming in some like that, and we know right at point C that it has this value of 17 kip feet. And then when it leaves and goes to the right, it might actually change, but the value does not.
Can you explain that one more time? Kind of
Which part?
with that whole figure.
It's just showing that as you move from the left side under a point load to the right side, your moment does not change.
Okay.
Now, the way it's behaving before and after can change, but there's no jump. Maybe this will help if I plot the same kind of characteristics, except this time we'll look at shear. You might see what I'm talking about. So I'm coming from the left side, and I have a shear of, 1.5? And then suddenly, I hit that force, and I pass out the other side at a shear of 1 kil. So you can see right here at C, what's the shear? Well, it can be anything between 1 and 1.5. Now, as a structural engineer, which one would you be more interested in?
1.5.
The 1.5. But just remember that. And then we've also kind of connected it to this thing, that it seems the change in shear seems to be appropriately equal to the load.
Is this one of those things like whenever you make an assumption, make an equivalent point load that helps to over-design structures?
That's an interesting point. Maybe. An equivalent force would create a larger moment at the center, a larger bending moment. So it would be a conservative approach. In this course, unfortunately, you don't get to make that choice. So if it's a distributed load or some other kind of load, you have to analyze that combination. Now, we always make concentrated equivalents to help us deal with distributed loads. And we'll probably see one of those pretty soon. So any questions about this? All right, I'll turn this off.